equal to 1, right? And then the F, IQ, again, IX, IY, IZ should be zeros, right?
Okay.
So now it is we should have this one done before the the Leeds Edwards boundary condition. So basically, originally we have the propagation, right?
Yeah.
And it is supposed to be the next step. It is the calculation of raw yield, right? Something like that. And right now, if we should have the first thing, it is set zeros, right?
Yeah.
So this one basically, whatever you have done not correctly, I will put a 0, okay? And then I will do the Leeds Edwards up, right? It
On bottom.
doesn't matter which one first,
Yeah.
right?
Okay.
Right? So that is the 3 things we need to add.
Okay.
One more thing, so I still have this one, F temp something. So if you can open one of the PDF file we have, so because it is once it is crossing the boundary, it is not the original F. So right now what we are saying it is if we have this one from, let's say this one, it is F temp, right? Let's say it is 0.287. So what what I wrote on the blackboard, it will come here, it will not hit right on a note, but what I'm saying it is 0.287. Right?
Yeah.
Same number, and then this one will be split partially here, partially here.
Yeah.
But if you look at let me see.
Okay.
So no
Not this one.
for the Leeds Edwards boundary condition, not our paper. So talking about
This one's?
I'm not exactly
This is
sure. Yeah,
this is the one I use for.
Yeah, okay.
This is 2020.
Yeah, let's see. Yeah, let's see the equation somewhere.
Okay. For which one?
If you can go up, look at the theory.
Okay.
Scroll it down and slowly.
Slowly.
Yeah. Keep going. Let's look at the equations.
Okay.
And
This one.
keep going.
Like this. Okay.
Yeah. Continue.
Okay. Leeds Edwards boundary condition.
This probably next somewhere. Yeah. Keep.
Go.
Slowly.
Okay.
Let's see. I'm not sure it's here. So now this is regular. I
This
think
one.
here.
Okay.
I think here. Okay. CASS. So this. Let me see the above equation. So in terms of that A, can I look at here? Do we have something over here? No. Okay. So this is for the particle crossing the boundary.
Yeah.
So this is for the particle, but it is. Okay. So anyway, we can do the simpler version first. So if you think about, so this guy crossing this. So what the concept here. So let's say this one comes at. Let me move this one a little bit more realistic.
Okay.
Let's say we have this top and we have this one. I'm not sure in D2Q5 it is F5, right? F5 temp. Let's say it is 0.287
Okay.
at this point. And right now it is leaving from, let's say, Ix equal to 79,
Okay.
right? So again, depends on the time, then we have different L. Let's say the L, move it back to here,
Okay.
and a little bit on this side. And let's say this is ix equal to 9 and this ix equal 10, right?
Oh.
So the L shift this one back here. So the idea it is this one, it is of the same thing, but it is coming from another, like, you know, another node from here. Okay, and this one is the image of this one.
Okay. Yeah.
Okay?
Yeah.
But because the shifted distance is not integer, so the distance, you know, if it is right integer, it will hit on this one or this one, right? But this one, it is a little bit, let me do the 45 direction, so it is basically coming from here, right?
Okay.
And so this one is this one is the image, so if we put this one, let's say it is A, and this is the image of A, right?
Yeah.
But real periodic direction is, you know, conditions, and if we say this one is P, and then next one over here we have a P prime, right?
Yeah.
So for this one, P and P prime are exactly the same thing. Everything exactly, right? But this one and this one, they are not. What is the difference? Because they have a distance by nz.
Yes, the shift, right?
So there is a velocity difference. This one is the velocity difference. So if we assume the shear flow is this way, right? So velocity A, so it has three velocities. Velocity A, you know, U direction, and the V direction, and the W direction, right?
Okay.
And they are related with the UA prime, VA prime, and the WA prime. So people assume that those things are the same. Those things are the same. In the Y direction, if, for example, if you have something going up and this one is going up, so Y direction velocity, Z direction velocity, they are the same. But X direction, clearly they are not, right? So what is the difference? It is gamma. So this one should be, if we look at this one should be faster, this one should be slower, right? So it will be, if this one, and then we should have again, I'm not exactly sure. It's the gamma NZ, right? It should be gamma NZ because this is the slope. This is the vertical difference, right? This one is how the velocity in X direction is going to change in the Z direction, right? So this is the total Z direction difference, right? So that means the flow situation here and here are very similar, but not the same. Not the same. And if they are not the same, so the F temp in the 5 direction, right, at A, right? And so this one technically, who is going to get here? This is the F temp in the 5 direction, but it is from A prime.
Yes.
Right?
Yes.
And so we have the 5 direction temp from A, but we do not have this one.
No.
Right? So that is what this equation is talking about in the next equation.
Oh, okay. This one?
No, next one.
Okay.
Yeah, here. See, it you know, it really, you know, depends which one you are talking. For example, if we say, it doesn't matter. So this is one, and this is a shifted one.
Okay, yeah.
So this is the velocity, basically kind of like the velocity A. It depends on, you know, you either you're going up, either you're going down. You may plus, you may minus, right?
Yes.
So this is the shifted one. So because of the velocity will be different, they will cause some difference in the density distribution.
Okay.
Because, you know, a summation of the density distribution with, you know, with lattice velocity give you the, well, give you the momentum, right?
Yeah.
So these two things, because u and with this kind of shear velocity and these two guys are different.
Yeah.
So what these two guys basically it is what we have over here, right?
Mm-hmm.
And so the f at a and f a prime will be different.
Yes.
But f and lattice Boltzmann are doing calculation for f's. So f's we do not know. We have no way to get the f. If we get the f, you do not need to do the calculations,
No.
right? So, but we need to know, we know this one because this one is going to leaving this point, and we need this one. So we must have something connecting those two guys. And the connection, as in many, lattice Boltzmann boundary conditions, it is assumption. The assumption here it is the lattice density distribution in the upper direction, one with velocity u, another one with u either a little bit more, a little bit less.
Yeah.
They assume the difference between these two guys, it is the same difference if we use the FEQ calculation.
Oh, I see. Okay.
Okay? Because, we need, so what we basically it is we need, we have F temp, if we're using our picture, right, at A, right?
Yeah.
And we need, but this one is not useful. We need this
the
one,
F
right?
prime.
We need,
F temp A prime.
yes, F5 temp
A prime.
at A prime,
Yeah.
right? But we do not know this one, okay? And what we know it is, we know UA minus UA prime, it is gamma dot
And
NZ. So this can be calculated,
Yeah.
right?
Yeah.
So that is the ULE, right? That
yeah.
is ULE. So what we assume it is, we assume the difference between these two guys are the same. We assume the difference between F temp, right, 5A and F5 temp
A prime.
A prime, right, equal to, this one is available, but this one how much it is, right? We assume it is the same. Let me make it easier. We assume F temp 5 at A minus F temp 5 at A prime, okay?
Yeah, equal.
Equal to F equilibrium 5 at A minus F5 equilibrium at A prime.
Yeah.
This one we need, to calculate this one we need the density, velocity at
yes.
A,
Yeah.
VA, WA,
Yeah.
right?
Yes.
So everything is available,
Yes.
right? This we can do.
Yes.
And this one, density should be the same, right?
Yeah,
Density is, say, put this one, so
Yeah.
density A, right? And UA minus gamma dot N Z,
Z, okay,
right?
yes.
And
Yes.
we have VA,
VA,
same. We
and
have
then
WA,
yeah.
right?
Yeah.
So this one we can calculate.
Ah, I see.
Right?
Yeah.
And now you say, this one is available, this one we can do, and then we can figure out this
That
one,
one, yes.
right?
Yes.
So remember in the previous writing I have F, IQ, IX, sorry, N left, IY,
Yeah.
IZ, right? And I said it is A times F temp, right? And then it is IX,
Y.
IQ,
IX, IY.
Right?
Yeah, I see.
So this is not exact correct.
Oh.
We should have,
Oh.
right?
Yeah.
Because right now if you look at here, and depends which one subtract which one, right?
Yeah.
And what I write, it is just this term. And actually we need this one. And the difference between one, this is the correction by the FEQ. So that is the, if we do this one, so it is, let's follow the equation, follow the literature. So it would be, so this is the new one, this is the original one. So we need this one, it's the original one plus delta F in the IQ.
Okay.
So this one basically, it is equation 19,
I see.
right?
I see.
Equation 19, it is the new, the one we need and the one we have,
Yeah.
right? So the one we need, it is the original one plus delta F. And the delta F, if we can see, it is that F IQ, it is the F IQ equilibrium with the density at, let me put A, U, A, V, A, W, A.
Yeah.
Which, let me make sure. So this is the fraction. So this is the original one with the new velocity one. So it should be in the reverse way. Or you can, if I don't want to write that much, it is minus plus Fi IQ equilibrium calculated from rho A, U A prime, V A, W A.
Okay.
So it should be minus. It should be minus. Yeah, minus. And then this, so basically the difference, it is A prime minus A. Because here it is A, because this one, it is from point A, right?
Yeah.
And this one is different from A prime minus A. So then you will have this one will be from A prime.
Okay.
So that is the same. That is
Yes.
the same. Okay?
Yes.
So so try to get them organized, okay? Try to get them organized, and do not, think about jump to the, the program to run that immediately, okay? And just think about how to put the program together, okay? And also look at the 3D program and identify where the modifications need to be, considered. Okay.
Okay.
And I will look at which computer I don't use very much, and I probably I will get rid of the files, and at least you can use the Windows system. It might be slow. It might be slow. Okay.
So if this week the things I'm supposed to do is first to remove the obstacle.
Yes.
Okay, and then after removing the obstacle, I do this calculation. I include, I do the body force equals to 0.
Yes.
And then again, I do this function.
You need this. You need to write these 3 functions, and then put this 3 function, call this 3 function after the propagation in the original program. Okay. So this. And this is already in the program. This is already in the program. Okay. And the next thing, it should be the before it should be the collision, right? And this one should be already in the program. Yeah. And the next one it will be calculated rho, U, FEQ, and this is already in the program. Original program, I'm not sure which one first. You will see this one, this one, this one. Or this one, this one, this one, right? It doesn't matter because it is a loop, right? Doesn't matter where, but the step it will be 1, 2, 3, or 1, 2, 3, or 1, 2, 3, right? So you basically kind of find where is right after the propagation, you need to put these 3 functions. Okay. So that is, you need to write these 3 functions, and after they are well written, and then call them in the original program. If everything is correct, we should have the share flow.
Okay. So I'm editing the code you gave us initially, right?
Yes. Yes.
And I'm editing the 3D.
Yes,
3D.
do the 3D because we do not want to waste our effort on the 2D.
Okay.
You know, eventually we need to do 3D.
Okay.
Eventually we do 3D, but the 3D, but in the y direction, make it thin because the y we do not need. You know, originally probably it is a cubic box. It is 100, 100, 100.
So I make it small.
Yeah, makes the y direction
Very
kind of
small.
4 or 5, something like that. And as I said, you may want to set the x and z slightly different. So and right now it's just we do not have anything. You can have a very small system, say nx, and even the nx we do not need to be very long. We don't need to have say 100. You can say just 10 or 12, and with the major difference in the z direction. Major difference in the z direction. And once we have, you know, once we have the shear flow, say it generated in this kind of very thin slide, and then we, you know, and then we can look at, you know, but right now when we do the programming things, and we do not need, you know, because x direction again it is simply repeating itself, right? So you may want to think about nx also like 5 or 6, and nz just ny just 4, and do the nz like 100, something like that. Okay. Yeah. Okay. So think about them, and yeah, we can talk later on, and yeah, but you know, I didn't look at your code exactly, but it seems you have done a very serious job. You know, yeah, we will look at them. Okay. Yeah, and so see here, you know, more or less it, you know, it needs to do the, you know, the shifted interpolation. You know, you need to identify. So you're starting from here, where you are going to land it, and it is between which nodes, how you're going to split. The only thing that actually is new, so when we talk, it is not the original one is going to come back. You need to modify a little bit, and the modification is this one. It is this equation. Yeah. We have an equation for this guy. We have, if you look at, you know, we can look at the FEQ expression. And you may even want to simplify definitely you can say I will calculate this term, do the subtraction, but also you can find simplify the calculation. Say just look at the difference. If we can keep going up, look at the FEQ expression, it should be somewhere. FEQ. That is Boltzmann. FEQ. Where is it? What is Boltzmann? No, this is probably before somewhere. Yeah, here. Yes, okay. Right? FEQ, and if you look at the FEQ difference, you may say, you are looking at the difference between these two calculations, right? And the one calculation, this one is the same. Oh yeah. Right? Yeah. This one is the same, and then you will say 1 minus 1, this term should be kind of cancelled, right? And not too much simplification, and I'm thinking that we probably can simplify this equation, but it really depends. If you look at, you know, I'm not sure, that is just what I'm thinking. For example, you have the E dot U, right? Yes. You have the E, you know, you may want to get a piece of paper and do the derivation to see if you can simplify this one a little bit more. So, so if we look at the FEQ I, right? It is rho omega I and 1 plus 3 times. Basically, C is 1, right? And it is E dot U, right? Divided, and EI and plus 9 over 2 EU squared. It is E and U all squared, right? Yes. And